Hello, this is Professor Berang. I am a faculty in mechanical engineering, and I'm also a licensed professional engineer in the state of Washington, and my area of expertise is thermofluids. In this video, I'm going to show you how to use EES to solve heat exchanger problems when it comes to LMTD method. So there are two ways to solve heat exchanger problems. There's effectiveness NTU method, and there's LMTD method. This video is about LMTD method. First, I'm going to go over LMTD method very quickly. My assumption is that you're already familiar with how it's done. Then I'm going to show you how to do it in EES using an elusive function in EES that is very, very useful. So let's get started. Make sure you subscribe to this channel to get the videos. I'm going to upload more videos this summer. Okay, so we're going to start with a problems. First, I'm going to show you a problem, then we're going to solve it and get the numbers and see how that works. Here's the problem. This is a problem that says it is a one pass, one shell. It's a shell and tube heat exchanger. So one shell pass, two tubes like this. It's a heat exchanger. And the Dow is available on the shell side and the tube side. So on the shell side, we have the cold fluid going in and the cold fluid going out. What it tells you is that the cold fluid is in the shell side. And the tube side has the hot fluid, and you have the hot fluid temperature going in and hot fluid temperature coming out. The overall heat transfer coefficient for this heat exchanger is given, 2,500 watts per meter squared Kelvin, and the contact surface, this number is also given here. So based on this, it says calculate the total amount of heat transfer from this heat exchanger. So when you take a look at this, let's see what we have. I mean, you can pause this video and look at the problem and read it and write down things if you want to. But the first step to solve any problem is just to make a list of what you have and what you don't have. So it looks like what we have on the shell side and the tube side, we know it is one shell pass and two tubes. Okay, that's good. We know that. The next thing we know is that we have the shell side T cold in and T cold out. And it's important to know that this is on the shell side, because when you want to find the correction factor, you need to know which is which one is, the shell and which one is tube. We have the T hot in and we have T hot out, and this is supposed to be on the tube side. Okay, that's cool. The overall heat transfer coefficient U is given. That's the number that is given here. And of course, the contact surface is also given, which is this number here, 5 meters squared. And what are we looking for? We are looking for the total amount of Q dot in terms of watts. How do we find this number? So we set the problem up, and now we're gonna, I'm gonna give you a quick introduction on LMTD method, very quick, like in probably 10 minutes or something, and the idea of the correction factor. And we're going to go to tables to find the right correction factor. Right after that, after we solve it by hand using the tables, I'm going to show you how you can actually find the correction factor in EES. That's going to be the interesting part. And that will help you if you want to design a heat exchanger. That's more comprehensive than this. So let's do that. Okay. First, I'm going to give you an introduction on how to use LMTD method. LMTD method can be used, the theory is derived for like a parallel double pipe heat exchangers, parallel and counterflow. So these two, probably you're familiar with that. How does that work? So I assume that you know what a double pipe heat exchanger parallel flow is. I assume that what a counterflow double pipe heat exchanger is before watching this video, and I'm going from there basically. So the equation, this is a case of what you can see here, this is a parallel flow double pipe heat exchanger. That's parallel flow. How do I know parallel flow? Because you can see the hot flow and the cold flow, both of them have the same direction. And the entrance for both of them is pretty much the same. Wherever the hot fluid is going in is the same place that the cold fluid is actually going in. So both of them on their left side, and cold is coming out from the right side and hot is coming out from the right side also. So this is a parallel flow double pipe heat exchanger. Now, if we know this, the general equation for overall heat transfer coefficient, Q dot, not the overall heat transfer coefficient, for the Q dot of heat exchangers, parallel flow heat exchangers, is U times AS times delta TLM of parallel flow, like this. The overall heat transfer coefficient times the contact surface times the LMTD log mean temperature difference for parallel flow. How do we define the log mean temperature difference for parallel flow? The way it works is, I'm going to clear up this picture one time, and then now you have delta T1 and delta T2, the way it works. So I assume that you're kind of familiar with Lmtd method. This is just a quick review, because the goal of this video is to show you how you can actually do this in EES without using those tables. All right, so how do we find delta T1? Delta T1 is basically, you look at one side, delta T1 is basically T hot in. Let's just write it this way. It's just T hot in minus T cold in, and delta T2 equals T hot out minus T cold out. Remember, whichever comes first here, I use the hot temperature first. For delta T2, that guy comes first also. So if you use the hot temperature for delta T1 coming first, and you got to use the hot temperature for delta T2, again, it shows up first. Now, can you do like delta T cold minus delta T hot? Yes, you can. But for both cases, left and right, you have to be consistent. Now, once you calculate delta T1 and delta T2, that is also, they're also showed here, then delta TLM parallel flow is basically just delta T1 minus delta T2 over Ln of delta T1 over delta T2. The unit of LMTD is also Celsius or Kelvin, whatever it is. You can see that the bottom, the denominator, doesn't have any units. So whatever the unit of the numerator is basically just the unit of the LMTD. Now that's how you find it. Okay, once you have it, again, as I said before, same equation. Once you have that, Q dot equals U times AS times delta T Lm of parallel flow, and you're done in that case. What about the counterflow case? The counterflow case, we can take a look at the counterflow case. That's not a problem. This is the counterflow case, by the way. Let me share that for you. Okay. So this is a counterflow. How do I know this is counterflow? Well, take a look at the direction of the flow, the direction of cold flow and the direction of the hot flow. You can see that the hot flow is supposed to be the tube side and the cold flow is supposed to be the shell side. And they are in the opposite direction. Another indication is that T hot in is on the left side, but T cold in is on the right side. On the other hand, we have T cold out on the left side and we have T cold, T hot out on the right side. They are not on the same side. If the inlet of both hot and cold are on the same side, that is parallel flow. If the inlet on the cold fluid is on the right side and the inlet of the hot fluid is on the left side, then that is counterflow. So what about delta T1 and delta T2? You follow the same, basically procedure. For that case, you look at the delta T on one side and delta T on the other side. So it's the same deal as before. So delta T1 becomes this delta T, what is shown here. It becomes T hot in. In this case, I don't have T cold in. Instead, I have T cold out. Okay, sure. And then delta T2 is T hot out minus T cold in. Let me move this a little bit down so my picture doesn't block potentially doesn't block these equations. So that's what you have. Once you have this, then you can calculate LMTD delta TLM for counterflow. Delta TLM for counterflow is whatever we just found here. Same equation as before, delta T1 minus delta T2, Ln of delta T1 over delta T2. Just a second. Oh, there you go. So delta T1 over delta T2. Same equation as before, you can see that. But the only difference is delta T1 in this case and delta T2 in this case are different from the parallel flow. How do we find the over the total heat transfer rate? Q dot is basically, again, U, overall heat transfer coefficient, times AS times delta T Lm of counterflow in this case. Problem solved. And you can find it in units of watts. Now, when you use LMTD method for parallel flow double pipe or counterflow double pipe heat exchangers, there's no such thing as a correction factor. So there is only one delta TLM that you need to find, either counterflow or parallel flow. You need to detect what kind of problem it is. If it is a counterflow, calculate the counterflow LMTD. If it is a parallel flow, calculate the parallel flow LMTD. And then put it in this equation, and you're good to go. There's no correction factor. However, we love to use this method LMTD for other geometries, such as cross-flow heat exchangers, such as shell and tube heat exchangers. Shell and tube heat exchangers that have one, shell, 2 passes, 3, 4 passes, or they have like 2 shell sides and like 4 passes, whatever they have. So it's that's the case. And for the case of even cross-flow heat exchangers, the fluids could be one unmixed, one of them mixed, and could be both unmixed. You can have all these cases. So if for these different types of heat exchangers, we still love to use the LMTD method. However, the equation is not as simple as this one. So what they did is they developed the theory for the other geometries, but we still use the same equation here. We just multiplied by 1 correction factor. So if you multiply by 1 correction factor, we should be good to go, and we don't have to use complicated equations. The only question is, where do we find that correction factor? So let me just write the theory for other types of heat exchangers that are not just a simple parallel flow double pipe or a counterflow double pipe. So let's take a look at the other types of heat exchangers. Here's what we do for other types of heat exchangers. We love to use the same equation. What's the equation? The equation is Q dot, total amount of heat transfer, is U times contact surface times delta T Lm. That's what I love to use. Okay, no problem. The only difference in this case is this delta TLM can be calculated using some sort of correction factor. This is a correction factor, times delta TLM counterflow. Oh, this is important. So when it comes to using LMTD method for other types of heat exchangers that are not double pipe parallel flow or double pipe counterflow, there is only one delta TLM that you calculate first, and that is the counterflow case. And then you fix that by multiplying it by some correction factor. Does that make sense? So one more time, when you have a double pipe parallel flow, you calculate the parallel flow, LMTD, and you use the simple equation. When you have the counterflow double pipe heat exchanger, you use the counterflow LMTD and you use the simple equation. If you have shell and tube, 1 shell, 2 passes, 1 shell, 4 passes, 2 shells, 4 passes, whatever you have, in that case, you calculate the counterflow LMTD, and then you multiply that LMTD by some correction factor, and then you put that number in this equation. You put that number in this equation, then you're good to go. The question is, where do we get that correction factor? That correction factor comes from some analysis that you can find them in some tables that I'm going to share for you. And then after this, I'm going to show you how you can find that correction factor using EES. So let's take a look at these tables to see how we can solve the problem we were given, because the problem we were given at the beginning of this video was, in fact, a shell and tube, 1 shell, 2 passes. All right, let's do that. Okay, so these are the tables where you can find the correction factor when you use LMTD method. When do we use LMTD method? the main difference between LMTD method and effectiveness NTU method is that normally you use LMTD method when you have the information at the inlet and outlet, both. So for the problem that we were given, we had the temperature on the cold side in and out, and we had the temperature on the hot side in and out. And even if you don't have all the information, if it is possible to somehow find the temperature on the cold side in and out both and hot side in and out both, maybe the problem gave you some other information that you could have used to find these temperatures at the inlet and outlet, then you can use LMTD method. Effectiveness NTU method is the opposite. Effectiveness NTU method, you can use it when you don't know the information at the outlet, not on the cold side, not on the hot side, but you know the information at the inlet. And then you want to predict what's going to come out of this, heat exchanger. So that's a different method, but that's not the discussion here. Just wanted to mention that. Now, these tables you can find in any heat transfer book. I got them from Cengel's 6th edition book. And how does that work? These graphs, if you take a look at these graphs, I have like 4 graphs here. This is the case for a shell and tube heat exchanger that is 1 shell pass and 2, 4, 6, whatever multi-pass of 2 passes, basically. The next case is basically 2 shell passes and 4, 8, 12, basically multiple of 4 tube passes. That makes sense because if you have like 2 shell passes, then it has to be either 4 or 8 or 12. You're going to multiply that by, that would be the number of tube passes, basically. And other cases such as the cross-flow heat exchanger, that you have both fluids unmixed in this case, and you can have a cross-flow heat exchanger with one of the fluids mixed and one of them unmixed in that case. So all these cases you can deal with. And what are the mixed, unmixed? That's not part of the discussion for this video. That's a different story. So we are focusing on LMTD. So we have 4 tables here, right? And these tables, or these graphs, they are giving you basically the, the correction factor. How do I find the correction factor? That's the correction factor. Okay, let's take a look at the process. This process requires us to calculate 2 things first, 2 parameters first. One of them is P, this one, and one of them is R. In fact, P is the x-axis. That's the x-axis is supposed to be P. And then R is another parameter that is these basically numbers that we can see here. R equals 4, 3, 2, 1.5, 1, whatever you can see on the graph. So the x-axis is P. You need to calculate the x-axis, and then you calculate R, and then you can find your graph. Let's say, for example, you calculated P, and P happened to be 0.8, for example, and you calculated R, and R happened to be 0.2. Then the way to calculate the correction factor is, okay, my P was 0.8, and my R was, I don't know, 0.2, and then now this is the right graph for me, so I'm doing a sloppy job here. And then this would be my correction factor. The correction factor is somehow about 0.86 or something, whatever you see here, right? So that's what you see here. Okay, this is just an example. And so what is P? What is R? How do we calculate that? Let me clean up this so I can go over how to calculate P and R. It looks like P is this parameter, this interesting parameter that we can see here, that is like these temperatures, T2, T1, T1. What are these? You see capital T and you see lowercase t. So for these cases, basically, that's why I told you at the beginning of this video that the problem needs to give us which side is the tube side, which side is the shell side. Because according to this table, the lowercase t's are the tube side, right? And the capital T's, these 2, are the shell side. And that's the same case with all of these graphs, basically. So all of these 4 graphs that you can see here, figures, they follow the same, they're consistent. They follow the same convention, right? So lowercase t is the tube side, and capital T is the shell side. So you have to keep that in mind. And what is in, what is out is 1 and 2. So T1, capital T1, is the inlet on the shell side. Capital T2 is the outlet on the shell side. Lowercase t1 is the inlet on the tube side, and lowercase t2 is the outlet on the tube side. One more time, 1 and 2 respectively are in and out. Lowercase t is the tube side, capital case T is the shell side. That's how you find the correction factor you're looking for. So if we have this knowledge, then we can solve our problem. So we can go back to that problem, calculate P and R, and once we calculate P and R, we can come back to these graphs and find the right correction factor and calculate overall heat transfer coefficient, not overall heat transfer coefficient, the total amount of heat transfer rate in watts. Overall heat transfer coefficient was given anyways. So let's go back to the problem that we showed at the beginning of this video. Okay, this is the problem we started with. So what is our job? We need to calculate P, we need to calculate R, we need to go to that graph, find the correction factor F, we put it in the equation, we find the total amount of heat transfer rate. Okay, so if you remember, just go back. How do we calculate, here's the question, how do we calculate P and how do we calculate R? So what was the equation for P and R? That's, you have to look at that graph to use the right equation. You can go back and watch that part of the video that had the graphs there, and you can find the equations. So I'm going to write them here. So P was supposed to be T2, lowercase t2, minus T1 over capital T1 minus lowercase t1. Okay? And as a result, let's just see what these values are. Well, lowercase t2 is on the tube side, outlet on the tube side. Which side is the tube side? Oh, this is the hot side. The hot fluid is on the tube side. So the fluid that is coming out is T2. So this has to be our T2. And this has to be our T1, lowercase. This has to be our capital T2, and this has to be our capital T1. Now we know what we're doing. Okay, cool. So T2 minus T1, that is 50 Celsius, minus T1, that is 80 Celsius. Don't worry that it's going to be negative. I mean, both of them, both numerator and denominator are going to be negative, so it's not a problem. T1 minus T1, what is T1? That T1 is 5 Celsius. I can see that. Minus T1, that is 80 Celsius. We calculate this, and if you go ahead and, you can pause this video and calculate this, you realize that P turns out to be 0.4. Happen here. 0.4, like this. Now, what is R? How do we calculate R? R is supposed to be, according to that equation we have on that table, capital T1 minus T2, like this, over lowercase t2 minus T1. Okay, let's do that. Then T1, that is 5 Celsius minus 50 Celsius, like this. And T2, that is 50 Celsius minus 80 Celsius. If you calculate this, it happens to be 1.5. Now, using these numbers, P 0.4 and R 1.5, we go to that table and we go to the graph and find the value of correction factor. Okay, first we need to know what graph we need to pick. The correct graph for our case is, the problem said 1 shell pass and 2 tube passes. And so basically this would be the first one is the graph we're looking for. So we're good to go. What did we find for the value of R, for the value of P? For the value of P, we found 0.4. And what did we find for the value of R? For R, we found 1.5. So it looks like actually we are in a good shape because we have this 0.4, and we're going to just draw a vertical line here until it hits this 1.5 curve. And then we go here. Looks like the value of correction factor is very close to 0.8. So we're going to use this value. Using this, going back to our problem, we can calculate the actual value of heat transfer now. So let's go back there. Here's the problem. So F is supposed to be 0.8, right? Now, what's the value of Q dot? Q dot is U times AS times correction factor times LMTD of counterflow. So I need to calculate the counterflow LMTD also. Okay, sure. I'm going to calculate that. How do you calculate the LMTD? And let's write it here. So I guess I have to. Delta T1 would be T hot in minus T cold out. Delta T2 is T hot out minus T cold in. I already calculated these values, so I'm going to put the numbers here for you. You can also calculate yourself to see what it is, because we are given all the values, just to save some time. So delta T1 turns out to be 30 degrees Celsius, and delta T2 turns out to be 45 degrees Celsius, like this. And once I have that, the problem is solved. Q dot happens to be overall heat transfer coefficient, which is given as 2,500 watts per meter squared Kelvin, times the contact surface, which is 5 meters squared, okay, times the correction factor, which happened to be 0.8, and times, let's write 0.8 one more time, 0.8 times the delta TLM counterflow. The delta TLM counterflow I already calculated. It happens to be 36.99 Celsius. How did I calculate delta TLM counterflow? I write the equation here for you. Delta TLM counterflow, you can calculate it yourself. It's delta T1 minus delta T2 ln of delta T1 over delta T2. You put all these numbers together, and eventually you can calculate the value of total amount of heat transfer rate. And that would be Q dot is, the value happens to be 371,470 watts. That's the value. So when you take a look at the answers that we have here, it looks like A is the correct answer, right? So again, I didn't show all the calculations. You can pause the video. You can use your calculator to calculate these things, to double check all these numbers, but I already double checked them. So now here's a fun part of this video. Here, the question is that if we take a look at the graphs that we had, it's not always the case that everything, you find the value of P, a really nice value like 0.4, and the value of, R 1.5, just like the case that we had here. So we get a really nice, case that directly I calculate the correction factor to be exactly 0.8, right? That's usually not the case. What if you calculate the value of, P to be, I don't know, something like, 4.41 or something, or 42 or something like that. So something like this here. Or I calculate the value of R to be between 2 and 1.5, something something like this here. Then is it possible to solve the problem? I guess in this case, it's not going to work. So let's say the value is like 35 or something, or 38 or something, 0.38. That could be one of these cases. So if that's the case, then I don't have a nice graph to find it easily. Also, when you are designing a heat exchanger, you are designing it, and you have certain values of, you're playing with these numbers of T1, T2 to see how that could work to accomplish the same amount of heat transfer that you want. You have to guess the value of, the correction factor if you want to use this equation. What can we do in that case? Do we have to do it by iteration to pick a value? I mean, that doesn't, it is possible, but it's not as convenient. Now, here's where I'm going to show you the elusive function in EES, and I will tell you why I call it elusive, that I can use here to find the correction factor very easily without using all these graphs, because that function covers all of these graphs. In fact, not just all of these graphs, the graphs that you don't even have here. Take a look at this. I do have the value of 2 shell passes, right? And 4, look at this one, like the second graph. It's 2 shell passes and 4, 8, and 12, 2 passes. Okay, cool. What if I have 3 shell passes, right? And if I have 3 shell passes, I will have 6 tube passes at least, right? That would be something. That would be something really interesting. 6 or 12, tube passes. What if I have 3 shell passes and 6 tube passes, or 3 shell passes and 12 tube passes? That's something that you can't find in this page. The Lmtd function in EES, in fact, has all the information that you want, and you can just use one function and find it. So let's introduce that function. If you are not familiar with EES, how EES works, I put a link in the description here that I explain how EES works in general. One of my videos, you can go back and watch that video first, and then you can come back here and look at the code that I wrote here. So here's the function we're looking for. The function that we're looking for is called Lmtd correction factor. That's what it is. So let's go to EES and take a look at it. All right. We said we want to use this equation, and what we are looking for is the correction factor. Okay, so one way to find the correction factor was those graphs. You go to the book, you find those graphs, you approximately find the value. Now, how do we find it in EES? In EES, there is a function we can use. This function is called Lmtd's underline CF. So the function in EES, I'm just writing it here for you and how it's going to work. The function in EES is called Lmtd. So that F in EES, you find it using Lmtd underline CF. The CF stands for correction factor. How does that work? The way it works is you have to enter 3 parameters in order to solve the problem. So let's say I want to find Lmtd correction factor for any, heat exchanger. It could be a, unmixed, one fluid unmixed cross flow, or both fluids unmixed cross flow, or 1 shell pass, 2 tube passes, 1 shell pass, 4 tube passes, anything, right? So use this function. First, here, you put the type of heat exchanger, which is a text, basically. You have to type it, and you're going to use quotations. And then you enter the value of P, same value of P that we had on those graphs, and same value of R that we had for those graphs. So the output of this function is that correction factor we're looking for. Once you have that correction factor, you calculate basically the Lmtd counterflow, right? And then you multiply that by this correction factor that you found, and that becomes your regular Lmtd you're looking for. And once you have it, Q dot would be U times AS times Lmtd, and you are good to go. That's your method. So looks like the function seems to be straightforward. Keep in mind that this is just an underline, right? And how do we define the type of heat exchanger? There are 4 types of heat exchangers that you can define for this basically function. And I'm going to write them for you. One of them is interesting because it's not supposed to be there, but somehow it is there. And I'm going to explain that at the end of the video. So don't worry about it. It might sound confusing. So just remove the confusion I explained at the end of the video. So how do we show the type of heat exchanger for this function? First of all, you have to write that between two quotations, single quotations, basically. So the flow, if the heat exchanger is a cross flow and both fluids are unmixed, cross flow underline both, underline unmixed. Unmixed. That's what you're going to type in EES. I'm going to show you there, so don't worry about it. That's one type. If it is cross flow, but one of the fluids are unmixed and the other one is mixed, basically you just write one unmixed quotation. If it is one of these shell and tube ones with one shell passes, you know, whatever it is, then you write shell and tube like this, and is just the and sign, and then underline, then you put a number here. This n, in fact, is a number. How does that work? N could be somewhere between 1 to 9. If n is 1, right, whatever n is on the shell side, on the tube side, it's either 2n or 4n or 6n or whatever that is, right? That's how you find it. So if n is 1, you can have 1 shell pass, 2 tube passes, or you can have like 4n, you know, 4 tube passes. You can have like 6 tube passes, just like that graph that we had. The graph said 1 shell pass, 2 tube passes, or 4 tube passes, or 6 tube passes. If n is 2, that would be 2 shell passes, and then on the tube side, it becomes either 4 or 8 or 12 tube passes. But what you see here is because n could be from 1 to 9, it covers the graphs that you don't even have in the book. You can put n as 3. If n is 3, the tube pass could be either 6 or 12 or, I don't know, 18, whatever that, or you know, whatever you're looking for, you can actually find that. So that's very, very, very interesting that you have, you know, this function. So that n is a number. There is another, you know, argument for this function that you can potentially use. And I'm going to explain that because I don't want to confuse you at the end of the video. So let's just take a look at these three. And let's go to a code that I wrote for the particular problem I showed you. And let's see how that works out. Now, it's going to be very interesting. So let's take a look at a code I wrote for this particular case. Let me share that for you. So this is the EES code I have. Look at this. So you can, you know, pause this video and just, you know, if you want to write this code in EES, just pause this video and look at the whole thing and just write it down in EES, and then you can run it and it works. Make sure that I use the basic SI. So if you look at the introduction to EES video that I posted, at the beginning, you have to check that your units are good. So for this code, I'm using basic SI units. Now I'm going to just even show you the units that we have. You go to options, you go to unit system. The unit system I'm using here is joules, is Celsius, and Pascal, and mass, and it's basic SI units I'm using. I can get away with Celsius because I'm not dealing with ideal gas law, things like that. So this works. Now, at the beginning of the code, I just type whatever we had on that problem. The shell side, the cold in, cold out, the tube side, the hot in, hot out, you know. And then the heat exchanger properties that were given. We had the overall heat transfer coefficient, and we had the contact surface. So I entered all of these values. All right, cool. Now, what's the next step? I had to calculate P and R, and based on whatever is given as shell and tube, I calculated P and R here, you know, in this part of the code, basically. And if you look at the rest of the code, basically, the rest of the code, after calculating P and R, I calculated basically here in this line here, the correction factor, using the function I just told you, Lmtd underline CF. CF is correction factor. The first argument is the type of heat exchanger. As I told you, there are 4 types of heat exchanger you can type. This is shell and tube and sign. You can't just type and. That's not going to work. Only the cases I showed you, shell and tube 1, because it was 1 shell pass, 2 tube passes. That part doesn't matter. It was 1 shell pass. And then P, the P that I calculated here, and then R, the R that I calculated here. It goes here. Is it possible to use other types of heat exchangers? Yes, absolutely it is possible. Other types of heat exchangers that you might be interested in could be like the cases I told you before. So other cases are, let's just to show how that works, I'm going to just type them. I'm not going to use that because that's not the actual problem, but it has to be between 2 quotations. You can use cross flow like this, cross flow, and both unmixed. You can use that, or you can say cross flow 1 unmixed. You can use that one too, or you can say shell and tube, shell and tube underline 2. Then that would be the case that you have 2 shells and you have 4 passes, 4 tube passes. You can have, I don't know, 3 of them, 3 shell passes and 6 tube passes, something like that. So it depends on what you're looking for. Our case, the problem asks for 1 shell pass. So this is the right type of heat exchanger for us. And this function calculates the correction factor for us. And once it does, I create the counterflow LMTD first. I have to calculate that. Let's take a look at it. So first, I calculated delta T1 here. You can see delta T1 is calculated here. And then delta T2 is calculated here. Once I have that, I put together the delta TLM counterflow. The counterflow case, because these delta T1s and delta T2 are for counterflow. Then delta T1 minus delta T2, ln of delta T1 over delta T2. And then you have the LMTD, which is the correction factor that was calculated here, multiplied by the counterflow delta TL. Once I have that, I have the total equation. Q dot is U times AS times delta TLM, and problem solved. So this will get the job done, basically. Now, all I need to do is to, at this point, is to run this. Okay, I'm going to run it, see what happens. So I run it, and this is what I get. So this is the answer. Q dot is 371,470 watts, or 371.5 kilowatts. But take a look at this. The most important part of this whole video is, oh, this is very interesting, because if you remember, I got the value of correction factor from that graph, 0.8, and I have the same value. This is really interesting. So I have a function that gives me what exactly I want. That's very, very, very nice. Here's the question that, what if this was a different type of heat exchanger? What you can do is that, based on the type of heat exchanger, you can go ahead and just, type those values, type the type of heat exchanger, like, I don't know, cross flow, both unmixed, cross flow, 1 unmixed, shell and tube, shell and tube underline 3, shell and tube underline 4, whatever you're looking for, then this function gives you what you want. There's one question. If you remember at the beginning of this video, I said this is an elusive function. Why did I say elusive function? Because if you go to help in EES and you try to look for this function, you can't find it easily. And I'm going to show you why that's the case. So let's take a look at the help index of EES and see what happens there. This is the help index of EES. And in the help index, if I type LMTD CF, I can't find it. I find other things like lithium chloride or water library. That's not what I'm looking for. I am looking for this function. So you might think that this function doesn't exist. This function does exist, but where do I find it? So one way to find it, if you're looking for help for it, you type heat exchangers. something like this. And we have heat exchanger library. So I'm going to click on that. And then if you go down to heat exchangers, there's heat exchangers, compact heat exchangers, there are a bunch of other things, radiations. You can, use that, pipe dimensions, but that's not part of this video. I go to heat exchangers, and then probably here it talks about, you can find effectiveness NTU method, because there are a lot of equations of effectiveness NTU method. You can find them in EES. That's a good thing. Log mean temperature difference, usage, and then you will find F equals Lmtd CF. So that's why I call it an elusive function, because easily you can't find it in EES. And then they explain what P is, or whatever I said. I think I did a better job explaining. But so you have P and R, same thing, and it tells you that there are 4 types of heat exchangers that you can type here in the function, and you can get the results you want. You have the cross flow like this, both on mix. You have the cross flow 1 on mix, and you have shell and tube. But look, there is another one here, parallel flow. Well, why do we need to have parallel flow for correction factor? There was no correction factor for parallel flow. Parallel flow, the correction factor was 1 if you use the right LMTD. Now I'm going to explain this to you, that how that works. That this part is a part that I told you that could be the confusing part about this function. It's not confusing. It is actually correct. So the way it works is, if you remember, the correction factor corrects the LMTD counterflow, right? So if you have a parallel flow double pipe heat exchanger, automatically first you calculate the correct parallel flow LMTD, right? That's what it is. What if you have a code that always calculates counterflow LMTDs, and you want to correct that for a parallel flow? You can either calculate the correct parallel flow LMTD without any correction factors. I'm going to write this down, so you see how that works. Or you can always calculate the counterflow, and even if the double pipe heat exchanger is parallel flow, you can multiply it by the correction factor that this function gives you and still get the correct answer. That part is pretty cool. So I'm going to explain it one more time, and then I guess we're pretty much done with this video. But this is an interesting part of this function that I really wanted to explain. So let's look at it one more time. Okay, we're back here. So I'm going to explain this one more time, tell you how this works. What I said before is, what if I have a parallel flow, parallel flow double pipe heat exchanger. I have a parallel flow double pipe heat exchanger. How do I calculate total amount of heat transfer? Q dot is U times S times delta Lm of parallel flow. Calculate the delta T parallel flow, and you should be good to go. What if you want to use the counterflow LMTD? In that case, what are you supposed to do? This equals Q dot, it is equals U times AS times F delta T Lm counterflow. That's what it is. This F, in this case, I'm going to write it big enough. This F would be LMTD, quotations, parallel flow, like this, quotation, P and R. That's what it means. If you somehow don't want to use the correct parallel flow LMTD, you can still use the counterflow LMTD, but you got to correct it with some correction factor, because EES will even cover that case. Normally, you don't need to worry about it, because you see this is a double pipe, so you already go for the parallel flow. You don't have to do this. But if your deal is that I always calculate the counterflow, okay, sure, and then If it is a counterflow double pipe, I don't need a correction factor. Correction factor is 1, and I'm using that counterflow LMTD for a parallel flow, then you have to correct it using a command like this in EES. That's the whole thing. There's nothing more in this. So and it's very, very, very interesting when you think about it, that even EES even covers this case. So I hope you learned something from this video, and make sure to subscribe to this channel to get other videos in terms of about heat transfer, fluid mechanics, thermodynamics. I try to upload more videos this summer as I have more time. Thank you very much. Have a wonderful day.